So the objectives for this segment are going to be using the ideal gas law to relate pressure, temperature, volume, and number of moles of gases at the appropriate conditions, determine the molar mass using the ideal gas law, and include molecular mass with the ideal gas law to relate densities to the other ideal gas properties. Okay, so let's dive in. Let's do a simple usage of the ideal gas law. A fixed volume gas bottle contains 0.650 moles of gas at 0.961 atmosphere pressure. We add some more gas. If the final pressure is 1.15 atmospheres, how many moles of gas were added to the bottle at constant temperature? Okay, so great. We think, aha, a gas. There we go. All right. So with an ideal gas problem, we take PV plus nRT. Great. And so now we want to say, what are the things that are constant? Well, it's a fixed volume gas bottle. Great. So volume's constant. And we said this at the end that we want to do this with the temperature constant as well. So one thing I like to do on these is to put everything that's constant on one side and everything that's not constant on the other. So pressure is not constant. Number of moles is not constant. So that would give us RT over V. So RT over V is constant in this problem. So that means if we have an initial pressure and number of moles, it'll be equal to the final pressure and number of moles. So right there, we've got the relationship that we need. The number of moles, the later number of moles is equal to P2 over P1 times N1 from the ideal gas law. So by isolating everything that's constant, we have a new equality. The P1 over N1 is equal to P2 over, there we go, over N2. Is everything consistent there? Yes, because then we just multiply by N, we multiply by N2 and N1, and we divide by P1 there. So that's the relationship we can get. So N2 is therefore P2. Now the important thing here is which one is 1 and which one is 2. It doesn't matter as long as we're consistent. So what we want to make sure is that we use the pressure that corresponds to a given N1. So N2, if N2 is the final number of moles, the one we don't know yet, then we need to make sure that N2 is the final one. Therefore, this here is P2 and this here is P1. That's P1 because it's consistent with the initial number of moles, 0.650. So that's N2. P2 is 1.15 atmospheres, and P1 is 0.961 atmospheres, and then N1 is 0.650 moles, and so the atmospheres cancel. Our answer is going to be in moles as we want it to, 0.778 moles. So that is the final number of moles, but it's not actually the answer because the answer said how many moles of gas were added. So the change in number of moles, which is what we want, which is N2 minus N1, which is going to be 0.778 minus 0.650, and that is 0.128 moles. So given that change of pressure and given the initial number of moles, we can figure out the number of moles that were added. So I didn't have to worry about Charles' law, Boyle's law, or anything. I just used the ideal gas law and identified what was constant. Okay, so what's the molar volume of an ideal gas at standard temperature pressure, which is defined as 0 degrees C in 1 atmosphere? Well, this volume is from PV equals nRT. We rearrange it and get that, and we rearrange and get that volume is nRT over the pressure. And what's our N? What's on 1 mole? We want the molar volume, the volume of 1 mole. So 1 mole, and then we have our pressure in atmospheres. So we should use an ideal, the gas constant at 1 atmosphere. 0.082058 liter atmospheres per mole Kelvin. And then 0 degrees C is 273.15 Kelvin. And that's all divided by, STP is defined at 1 atmosphere. Can't really read that. 273.15 Kelvin divided by 1 atmosphere. And this gives us 22.414 liters. So 1 mole takes up 22 liters, which, a liter, think about 4 liters to a gallon, so about 7 gallons of milk. That would be about 1 mole of ideal gas. So a mole of ideal gas, that's like 20, remember, since water is 1 gram per milliliter and a mole of water is 18.02 grams. So that's about 18 milliliters of water. You boil that, and that will take up about 7 gallon jugs. It's a lot larger volume than that. So large volume expansion going from 0.018 liters to 22.414 liters. Okay. So is this, how accurate is the ideal gas law? Well, if you look at the molar volume at STP of some real gases, so ideal gas molar volume is 22.414 liters. The molar volumes of some real gases at STP, if you look at that, a lot of them are really right on. Ammonia is off, only in the 4th decimal place. Argon, pretty close as well. Chlorine is a little bit off. That's one that, it's off in the 3rd decimal place, but it's still within 2% or so. And everything else is really, within 0.5%. So it's a pretty good, it's a useful approximation that's very easy to do. And a room temperature, and that's, higher than STP, that's even better. So it's a good approximation. Oh, one thing, let's go back here one more page. Yeah, there we go. How many significant digits are here? I wrote this out for 5 significant digits. 1 mole and 1 atmosphere are exact numbers here because it's at STP. So STP is defined as exactly 1 atmosphere, and it's the molar volume, so it's defined as 1 mole. So even though I've only written 1 there, it's an exact number. And so if we look, we've got 5 digits of precision in the gas constant and 5 significant digits in the gas constant, 5 significant digits in the temperature, and therefore it's 5 significant digits. And one more thing to look at, remember 0 degrees C, in PV equals nRT, the temperature is the temperature in Kelvin. It's not the temperature in degrees C, it's the temperature in Kelvin. Think of it this way, that if you cool something down, if there really was point particles, if you cool them down so there's no motion at all, they stop colliding, that is the point where the volume goes to 0 when they stop moving. And so any temperature scale that doesn't have absolute 0 at the point 0 doesn't make any sense, because it means that you could get like negative temperature, you could get negative volume things. So you want, whenever you use PV equals nRT, you need to use temperature with a scale where absolute 0 is 0 and not a negative. You don't use a 0 of the temperature as something like the freezing of water. So always remember PV equals nRT, the temperature is in Kelvin, not in degrees C. Okay, so important reminder there. Okay, let's think about, can we use ideal gas law to find the density of something? So it's the density of ammonia in grams per liter at 0.898 atmospheres in 55 degrees C. Okay, 55 degrees C, remember we have to take and convert this into 15 plus 55 equals, now we only have 3 significant digits here and only 2 in the temperature there, so, but we're adding it with an exact number, so we'll get 3 significant digits here, 328K. So 328K is our temperature. So what do I do? Density. Density isn't in PV equals nRT. That's why there's no density there, but there is. It's hidden in there, because if we have PV equals nRT, what is density? Density is the molar density would be N over V. So PV equals nRT can be rearranged till N over V equals the number of moles per unit volume is P over RT. So we have a molar density, which is 0.898 atmospheres over 0.08206 liter atmospheres per mole Kelvin. And then we have 328 Kelvin. And this is important here, the kelvins cancel and the atmospheres cancel. Whenever you're doing these ideal gas problems, pay careful attention to the units, make sure the units cancel. You can catch a lot of errors that way, accidentally putting the R on the top when it should have been on the bottom. Cancel out the units carefully. So we get 0.0333 moles per liter. Liters in the denominator, mole is in the denominator of the denominator, so it goes up to the numerator. So that is our molar density. So our mass density, it's usually written as rho. Rho is equal to 0.0333 moles per liter, and the molar mass of ammonia is 17.03 grams per mole. And so the moles cancel, and that gives us 0.568 grams per liter, a little more than half a gram per liter of gas. So that's how, so density, we talk about, PV equals nRT relates these quantities. It relates density as well, because density is a function of the quantities that it relates. So we get that for free as well.